We're going to now look at the program that we've been talking about, this simple square drawing program, and go through the whole WebGL version of it. In this, I'm going to break this up into two parts. In this part, we'll very quickly look through the code, both for the HTML file and the JavaScript file, and then in the next lecture, we'll talk about some of the things we left out relying on default conditions, for example, the initialization in a little more detail and some of the viewing issues. But now we just want to look at our program. We'll see our shaders for the first time. We'll introduce a structure that we want to use. And this is the structure we, first here's the, just to see that it really does run on WebGL. There's just a snapshot from my browser, and again it's just a square inside of with a black background inside a rectangular window. Now we said last time what we're going to do is go through 5 steps for developing our applications. We're going to break things up into 2 files, an HTML file and a JavaScript file. The JavaScript file will be read in by the HTML file. The HTML file will be the file that will be loaded when you click on the URL for your project. So the reason we break it up is I'm trying to define the graphics, or keep the graphics in one file, all of the processing, essentially what the application is about, in the JavaScript file, and use the HTML file to do various initialization steps, to read in other files that are needed, and to describe what the page looks like. And I find that I've found it much easier to do things by organizing them in this way. You'll be welcome to use some other organization if you find it better. But the first thing we do is we're going to describe the page, what the request a WebGL canvas, which is going to be the drawing surface that we use, and read in some utilities and the JavaScript file. We're going to put the shaders, for now we'll put the shaders inside of the HTML file. I'll show you later, and it's in the book, how you can do that by putting them in a separate file, assuming that your browser will allow you to do that. Then in the JavaScript file, we're going to compute our data, then send the data to the GPU, and finally tell the GPU to render those data. Okay, so let's start with the HTML file. And it's pretty straightforward. The next slide will show you all the steps, but let's go through them in words here. Here are the 2 shaders. Okay, this is the first part of it. First, we say it's an HTML file. What an HTML document is, this line is probably isn't really necessary. It's saying it's an HTML file, but here it says what follows. This is a tag. It's an HTML tag. It says what follows is the HTML is in HTML. We can divide this this file into a couple of parts, into a head, generally into a head and a body, and we'll see examples later where we have other divisions. Once more, even if you leave out the head, it'll probably be just fine. The 2 important things: one, we say it's HTML, and second, we say what follows next is a script tag, which says a couple of things. First, it gives it an ID, and the reason it's giving it an ID is that I want to be able to refer to it in the JavaScript file. So this ID is associated with this script, and it's just saying it's the vertex shader. We only have one, so we can just say vertex shader. And then it says, well, what is the encoding in the script? What's it going to follow there? And it says it's a vertex shader. This is understood by any HTML5 that understands a WebGL. So it's saying this is the type of information that's going to follow. And here's a very simple shader. In fact, it's about the simplest shader you can have, and since you have to have it, you gotta have something here. What it's doing is, this is what's called a pass-through shader. It's taking something called vPosition, which is an attribute. This means that it's being passed in from the application program, and it's a vector 4. So think of it as just a simple array with 4 elements in it, which are the X, Y, Z, and in graphics we use 4 dimensions most of the time, W, and that's the position of attribute of the vertex. And all it's doing is outputting it. This GL underscore position is what's called a built-in variable that is known by WebGL and GLSL and says that's the expected output position. The main job of the vertex shader is always going to be to output a position in clip coordinates so that the rasterizer can handle it. What we've done in this example to sort of cheat a bit is to make the input values automatically in the default clip coordinates so that we don't have to do anything except copy the incoming vertex position into the output vertex position. And then we have another tag here that says that's the end of this script area, and that's the end of our shader. Now we have a fragment shader, which once more has an ID, so we can refer to it in the JavaScript file called fragment shader, and the type is saying this is a fragment shader that follows. This is once more a very, very simple shader. All it's going to do is color everything white. So let's look at, I'll come back to this at the top in a minute. Notice too that both the fragment shader and the vertex shader are complete programs. They have a main. They could actually call other functions that you might want to write for complex shaders. So it sort of has the structure of a standard C++ program. Now here we have another built-in variable, the one that's required on the output side, which says what the fragment shader must do is provide a color for that fragment. Now underlying this is that every fragment has a position, and if I need that position, I can obtain those values. We'll see examples of that later. But all that this fragment shader is going to do is set every fragment to have a color of white, and we do that by setting the red, green, blue A values. The A is known as the opacity value, which says if it's 1, it says this surface is solid and no light passes through. You don't see anything behind it. And red, green, and blue 1 says that they're fully on. These values range between 0 and 1, where 0 is the least of that primary and 1 is the maximum. So this says red is fully on, blue is fully on, green is fully on, and we add red, green, and blue together, we get white. The vec4 here is a standard C++ type constructor. It says make a vec4 with these as the values. This is why we've used vec4 as one of the atomic variables in GLSL. Remember we said it includes both matrix types and vector types for 2, 3, and 4-dimensional entities. This is a vec4, and we use vec4s, as we'll see, in vec2s and vec3s in the MV package that we've developed to go along with this course that you will use on the application side. So we're trying to match it. Now finally here, the precision is required in GLSL. You don't use this in desktop GLSL. But the reason for this is that because this is coming from OpenGL ES, the embedded systems one, many of the devices that ES supports are very simple devices, low power devices that don't support very complex frame buffers or very complex arithmetic computations. But the rule is that it has to at least support what's called medium precision for floating point variables. That's 32 bits, I believe. There's high precision and there's low precision, but the requirement for WebGL and ES is that everything must at least support medium precision, but you must include this line in your code or you'll get an error message in. So every fragment shader should have this. If you want to do something that's a little more complicated, you'll probably never notice the difference in simple applications of saying high P versus medium P, but you can put in high P and see if it runs. It'll run. Virtually every browser will run high P. Or you can even put in a compiler directive that says if it supports high P, then use high P, otherwise default back to medium P, and you'll see examples of that. But for everything we're doing in this class, medium P should be fine, but you really need to have that in there. Okay, so these are the things that we saw. We assigned names to the shaders because we want to use them in the JavaScript file. We had two simple pass-through shaders that did very little, but they were required to set GL position in the vertex shader and GL frag color in the fragment shader. Okay. We could have used the vector vec2 instead of vec4 because this is a two-dimensional example, although what happens is that everything is four-dimensional, and if you type of, say something's a vec2, it will put it inside of a vec4 automatically in WebGL. Okay, now let's look at the rest of the HTML file. The rest of it does two things. First, it reads in a number of files that are in JavaScript, and second, it asks for a canvas. So let's look at the first part, what we're reading in. Script again, the script tag, and it says what follows is going to be in JavaScript. That's the type. And where is it coming from? It's coming from a file that I've put in the common area of our website, which are the standard utilities that are used to set up the canvas. These were, I think, originally done by Google, but they run on all the browsers. And it's fairly simple. It allows you to easily set up an OpenGL context, which we do down here, and then we have an end script tag. Then we read in a function that I'm giving you called init shaders, and I've given you that for one reason, which is to just simplify the initialization of a program and not get hung up on a lot of bookkeeping kinds of routines that are necessary. So all of the routines that read the shaders in, convert them into the right format, then compile, check for errors, link, and form what's called a program object, are all inside of this JavaScript file, which are, it's in the first appendix, which I'll make available to you. But it's basic code that's going to go in every single program, and I don't want to get into the details of it now. Third thing we read in is a package that we put together for this class called mv.js, standing for matrix vector, which tries to mimic the types that are in GLSL. So that's why we have vec2, vec3, mat2, mat3, mat4 in there. Plus, it has a lot of functions that we'll use later to do our matrix and vector algebra. So to multiply, to form various kinds of matrices, to do viewing. We'll talk about all those later, but we've put them inside of this little package. And finally, we read in our application code, and that's we're going to call that for this example square.js. Then we're finished with the head, and again, if we left out head and end head, we would be just fine. Here's the body of the, once more, we could leave out body and end body. But now here's the key step. We're going to open up a canvas, and we're going to give it an ID once more so we can refer to it in the JavaScript code, and give it a height and a width in pixels. So we're saying I want a 512 by 512 canvas on the screen. If your browser doesn't support WebGL and the canvas element, then you're going to get this message and everything will end. Otherwise, at this point, you're done with this part of the JavaScript, and the execution will now go on to the JavaScript application in square.js. So to review, the WebGLs are standard utilities to set up a WebGL context and they're in this common directory on our site. Init shader sets up the code for reading and compiling and linking our shaders, our package, and the particular application. So basically, what you're going to change in any other application is really just change the square.js to whatever your application is and put in the shaders that you're going to use instead of the trivial shaders that we just looked at. Okay, now let's turn to the JavaScript file. All JavaScript file is going to do is do some initialization, then form the data, send it over to the GPU, and then render those data. So let's see what we do. We're going to have two variables here. One is the GL context, and then the points that we're going to send to the GPU, so we set them up. So now what's happening here is window on load. Window is known outside of JavaScript. Scoping in JavaScript is different than it is in other languages, and window is something that is defined outside and is known at that point when you open up when you've opened up the window in the HTML file. So we're saying when that's loaded, the other issue that's going on here is the execution model in HTML is different from what you're probably used to in with standard programs that call functions, and or if you've ever done OpenGL in C and C++. What happens in JavaScript is that or let's say in HTML, is all of these files are loaded in. If there's an error, something will happen, but they're loaded in asynchronously, one after another, and then it's looking around for something to do or waiting for an event. What the onload method does is say, when all of this stuff is loaded in, then I want you to execute this function init, and here's the function right after that. This is again a little JavaScript construct where you name the function and you define it right after. Functions are first-class objects in JavaScript. So this is just saying, here's the first thing I want you to do. I want you to run this function init, which I'm giving you right here. Okay, here's the canvas that we're going to draw on. Where is it? Well, I define that back in the HTML file, but I can get its ID using this method, getElementById. Once again, document has been defined outside of this program, and get me the element GL canvas, which we defined back in the back in our HTML file. Then I set GL equal to this canvas using the utilities that I read in the HTML file. If it doesn't exist, then I simply exit. But this sets up what's called a WebGL context. What you can think of GL as being is the canvas that can run WebGL, plus all of the functions and parameters are all in there as methods or constants, and you'll see how we refer to them later. So even though we're calling functions like gl.clear, gl.something else, it's because we call the GL context GL. You're welcome to call it something else. Okay, so that includes everything we need now to run our WebGL app. So we define 4 vertices, which are the corners of the square. We're rigging the coordinate system so that it'll come out as a nice little square inside the region we just defined back in the HTML file. We'll talk about that in the next lecture. But there's our 4 vertices. So onload determines where we start execution once everything's been read. We got the canvas context from the HTML file. And then the vertices, as we see, are using the vec2 type. Okay, so I just give them essentially the x and the y value for each of those. These vec2 types are not basic to JavaScript. They're defined inside the mv.js package, but they look like the same types that are in GLSL. Okay, one of the things to keep in mind here is that we form this array, and it's not a C or Java array. That is a really key point that we're going to see more in the next slide. That's one of the gotchas that you're going to find in JavaScript, because the code looks a lot like what you would do in C, C++, or Java, but everything is an object in JavaScript, with the exception of numbers and strings. But everything else is an object, and objects have methods, and they inherit those methods from some base classes that are outside of your program. So for example here, where I define vertices, it looks like a standard C, C++ array, but it's not, because, and it's more than just that I've used vec2 here, because I could have just given it this string of all 8 values here and defined an array, a JavaScript array this way. This array has methods that are attached to it automatically, and so if you look at something like vertices.length and say x equals vertices.length and look at x is going to be 4. It has 4 elements in it, 4 vec2s. So this is going to be a problem, as we'll see in the next slide, when we try and send things off to the GPU, because that expects very simple things, not what's essentially a structure with different elements attached to it, and not in the right format that WebGL wants to see. Again, repeating that the values are in what are called clip coordinates, because that's what the rasterizer expects to come out from the vertex shader. Okay, final part of the code looks like this. We're going to decide what part of that 512 by 512 screen we want to use, and this says I want the whole thing. I want something that starts at the lower left corner, 0, 0, and has the full width and height of the canvas that I defined back in the HTML. So this says I want a 512 by 512 image on the output. Now here's and notice, see, here's a function that refers to the GL context, GL dot, and it's the function viewport. Second one sets a color to clear the screen with, and I'm setting it to be no red, no black, no red, green, blue, and I'm going to make it opaque. So this is saying I want the clear color to be black. So when I clear that screen or window, it's going to give me a black window. Okay. Now I'm going to load the shaders. Okay, let's see what I do here. Here's the program init shaders that I'm giving you, that we read in the JavaScript file, and I'm going to give it the WebGL context and the names of the shaders, which are the names that we got from the HTML file. And then what this function does is all of the compiling and linking and checking, and it returns a variable which is called a program. Now that program, I'm calling it program, but the idea is it's called a program object. And the program object is a container that contains all your shaders. You may be using more than 2 shaders. You may be changing shaders as your program goes on. And so you put all of these things inside of a program object, which is what's linked within the execution of init shaders. And then we say, use this program. Now, the reason for that is I could have multiple program objects and switch between them, which we'll be doing later when we start talking about rendering to texture and applications like that. So we can have multiple program objects, and it says this becomes the present program object, which contains the shaders that I'm going to use now. Okay, now we're going to load the data onto the GPU. How do I do that? Well, I have to create a buffer on the GPU, so I have a function GL create buffer, and returns an identifier for that buffer. I then bind that buffer. Now what the bind does, give it an ID. This says this is the present buffer. So there's there's always a concept in WebGL and OpenGL of the current or present state, and this is saying that the current buffer, whenever I refer to a buffer, is going to be this buffer that I defined over here. Obviously, in this example, I only need one, but in other applications, we'll have multiple buffers, and every time I do another bind, I could change which buffer is being used as the current buffer. Now that buffer has been created. It has a size, but it has no data in it. And array buffer is the type of buffer that I'm creating on there. That's the kind you'll be using most of the time. So I send data now out there. So I'm sending data out to an array buffer. That's the type of buffer out there. I have the present buffer. It's the one I just created up here. And I want to send out the vertices. Now, because the vertices are not a simple array of values as they would be in C++, that's a problem for OpenGL or WebGL. So what I have is a function inside of the MV package called flatten, which will extract the values and make a simple array and pass that in. If you don't use flatten, you're going to get errors because it's not going to see what it expects to see when this thing is when these data are loaded onto the GPU. The static draw constant here is just a hint to the GPU as to how I'm going to use the GPU in this example. The GPUs are getting very smart, and they can organize their own memory in complex ways and have multi-level memory structures. This is just a hint saying, in this example, I'm not going to redraw it over and over again. I'm not going to keep loading data into that area. So it's a static draw as opposed to a dynamic draw. And on some GPUs, that's going to make a difference. Okay, now I've got this area and these vertices on the GPU now. I've sent the data over, but I have to now associate that with variables that are in the shader program, because the shader doesn't know anything about these data in this buffer. So now I'm going to associate shader variables with what's in our buffer. In other words, I have two programs here I'm talking about. I'm talking about the vertex shader and I'm talking about the application, and now I have to make that association. So what I'm going to do is define a variable called vPosition. The V here is standing for, it's give you the hint that this is referring to something that's on the vertex shader, in the vertex shader. And it says, get me that location from the program object I created up here and look for something in the shader that's called vPosition. Another way to look at this is when init shaders does its linking, as in any linking that goes on, you'll have tables internally that will say where variables are located. So this is sort of saying, go into those tables and find where vPosition is and tell me that and put it in this variable so that I can use it in the application. Okay. Once I have that, I can now start talking about what format that data is in, because the shader needs to know that. So here's vPosition. It's saying, okay, create something called an attribute pointer and an attribute array. And what I'm going to do is say each element there is of dimension 2. Remember, those were vec2s. They were floats, and you can do automatic normalization. I don't want to do that. I wanted to just take the values that I have, and the values here have to do with the offset, and we're not offsetting anything or worrying about interleaving of variables, so these two variables can be zeros for now. And finally, I have to enable the facility, which is called a vertex attribute array. And what we're saying is that we can send all kinds of information over to the GPU. If they're attributes like the position, the color, later the texture coordinates, they go in as vertex attribute arrays, and this one is vPosition. Later we'll have vColor, vTexture coordinate, but now we're just sending these over. So this is sort of a new concept if you haven't done shaders, but it will always be of this kind of a format. So we use init shaders. We form what's called a vertex buffer object on the GPU. We need to use that flatten function, and we need to do this connection mechanism that we had in those last couple of lines of code. Okay, now finally we have to render. Now the data are formed, they're on the GPU. Now we just have to do a render. That's simple. So we simply have last line in here is to just render. This is still part of init. It says when you finish with all that stuff, execute the render function. Here we only have to execute it once. It's a static example. And it says render. The render first clears. So we clear this color buffer bit as a constant that refers to the color buffer in the frame buffer. We want to clear it. It gets cleared with the clear color that we defined above. And finally, our drawing command is one line. It just says draw those arrays, the ones that are active. And we have one array that we enabled. It's just positions. And how do I want you to draw it? I want this GPU to draw it as what's called a triangle fan. We'll talk about that now, starting with the first vertex 0 and using 4 vertices. Okay, it'll draw a more complex thing if we had loaded more data in. Let's just look at what triangle fan is. Triangle fan, and again, this is in your, it should be in your notes, and you should be reading this now, says that form a sequence of triangles where the first 3 vertices, 0, 1, 2, first, second, and third vertices, determine a triangle, and then successive triangles are formed each time you add another vertex, but always using the previous vertex and the first vertex. So the first triangle is 0, 1, 2. The second triangle is 0, 2, 3. The previous 3 is the new vertex, 2 is the previous, and you always keep that first vertex, so you get this square out of 2. So remember that WebGL doesn't know about squares, it doesn't know about polygons other than triangles. So we have to draw 2 triangles. Now, what the advantage we've got out of doing it this way is we get to reuse vertex 2 and vertex 0 in this second triangle, so we only have to send 4 variables over instead of 6 as we would if we drew the 2 triangles separately, a 0, 1, 2 and a 0, 2, 3. But there are 2 alternatives to this, and I'll just give you that now, is that if we did it in that simple way, I could use GL triangles. Now GL triangles says, for all the number of vertices I give you, take each group of 3 and make a triangle out of it. So if I give it vertices 0, 1, 2 and 0, 2, 3, then I could get these 2 triangles again. Okay, of course I could do it other ways, but this would be dependent on the order in which I place the data onto the GPU. It's referring to the order of the vertices in that buffer that I created. The other alternative is to use what's called a triangle fan, in which you use the first 3 vertices again form a triangle, and then the last 2 plus the new one plus the previous 2 form the second triangle. So you get 0, 1, what did I do here? I drew this wrong. It should be 0, 1, 2 gives you this one, and then, yeah, this one, oh, I'm sorry, let's do it down here. I'm sorry, we did triangle fan, and that was okay. That's over here. This is correct, sorry. GL draw arrays triangle strip, you want to have a different order. You want to have them as 0, 1, 3, then you get the first triangle, this green one here, and then the next group will be add on 1 vertex plus the previous 2, so you get the triangle 1, 2, 3, and that's what you would get with a triangle strip. But notice that you had to put the data onto the GPU differently, in a different order, if you wanted to use triangle strips versus triangle fans. But you should always keep that in mind for big problems, because you save not only a lot of time in transferring the data from the CPU to the GPU, but you also are much more efficient in rendering these triangles, because you're going through a much smaller buffer. Okay, so in the next lecture we'll talk about some of the things that we sort of accepted here as defaults, like the coordinate system, and what about the camera you talked about in the synthetic camera model. We'll talk about that in the next lecture.